In Chapter 20, we introduced the term semiconductor, which is a name given to materials that have an electrical resistivity intermediate between conductors and insulators. Semiconductors are commonly composed of the elements of silicon and germanium. However, they are not chemically pure, but instead intentionally contain a small number of impurity atoms. As we will see, these impurity atoms add extra charge carriers, which decreases the resistivity in these pure insulators. The figure shows an array of atoms that symbolizes the crystal structure in pure silicon. Each silicon atom has 4 outer shell electrons, and each electron participates with the electrons from neighboring atoms in forming the bonds that hold the crystal together. Since they participate in forming bonds, these electrons generally do not move throughout the crystal. Consequently, pure silicon and germanium are not good conductors of electricity. It is possible, however, to increase their conductivities, i.e. reduce their resistivity, by adding tiny amounts of impurity atoms such as phosphorus or arsenic, whose atoms have 5 outer shell electrons. For example, when a phosphorus atom replaces a silicon atom in the crystal, only 4 of the 5 outer shell electrons of phosphorus fit into the crystal structure and participate in the bonding. The extra 5th electron does not fit in, and it is relatively free to diffuse or move throughout the crystal, as Part B of the drawing suggests. A semiconductor containing small amounts of phosphorus can therefore be envisioned as containing immobile, positively charged phosphorus atoms and a pool of electrons that are free to wander throughout the material. These mobile electrons allow the semiconductor to conduct electricity. The process of adding impurity atoms is called doping. A semiconductor doped with an impurity that contributes mobile electrons is called an N-type semiconductor, since the mobile charge carriers have a negative charge. Note that an N-type semiconductor is overall electrically neutral, since it contains equal numbers of positive and negative charges. It is also possible to dope a silicon crystal with an impurity whose atoms have only 3 outer shell electrons, for example boron or gallium. Because of the missing 4th electron, there is a hole in the lattice structure at the boron atom as the figure shows. An electron from a neighboring silicon atom can move into this hole, in which event the region around the boron atom, having acquired the electron, becomes negatively charged. Of course, when a nearby electron does move, it leaves behind a hole. This hole is positively charged, since it results from the removal of an electron from the vicinity of a neutral silicon atom. The vast majority of atoms in the lattice are silicon, so the hole is almost always next to another silicon atom. Consequently, an electron from one of those adjacent atoms can move into the hole, with the result that the hole moves to yet another location. In this fashion, a positively charged hole, which is the absence of an electron, can wander throughout the crystal. This type of semiconductor can, therefore, be viewed as containing immobile, negatively charged boron atoms and an equal number of positively charged mobile holes. Because of the mobile holes, the semiconductor can conduct electricity. In this case, the charge carriers are positive. A semiconductor doped with an impurity that introduces mobile, positive holes is called a p-type semiconductor. There are many different electronic devices that are based on the physics of semiconductors. Let's look at one of these, called a diode. A diode utilizes a p-n junction, which is formed from a p-type and n-type semiconductor. The p-n junction between the two materials is of fundamental importance to the operation of diodes and transistors. The figure shows separate p-type and n-type semiconductors, each electrically neutral. Panel A shows them joined together to form a diode. Mobile electrons from the n-type semiconductor and mobile holes from the p-type semiconductor flow across the junction and combine. This process leaves the n-type material with a positive charge layer and the p-type material with a negative charge layer, as Part B of the drawing indicates. The positive and negative charge layers on the two sides of the junction set up an electric field E, much like the field in a parallel plate capacitor. This electric field tends to prevent any further movement of the charge across the junction, and all charge flow quickly stops. Suppose now that a battery is connected across the p-n junction, as shown in the figure, where the negative terminal of the battery is attached to the n material and the positive terminal is attached to the p material. In this situation, the junction is said to be in a condition of forward bias, and, as a result, there is a current in the circuit. The negative terminal of the battery repels the mobile electrons in the n-type material, and they move toward the junction. Likewise, the positive terminal repels the positive holes in the p-type material, and they also move toward the junction. At the junction, the electrons fill the holes, and in the meantime, the negative terminal provides a fresh supply of electrons to the n material, while the positive terminal pulls off electrons from the p material, forming new holes in the process. Consequently, a continual flow of charge and hence a current is maintained. Now, as the figure shows, the battery polarity has been reversed, and the p-n junction is in a condition known as reverse bias. The battery forces electrons in the N material and holes in the P material away from the junction. As a result, the potential across the junction builds up until it opposes the battery potential, and very little current can be sustained through the diode. The diode, then, is a unidirectional device, for it allows current to pass only in one direction. The graph shows the dependence of the current on the magnitude and polarity of the voltage applied across the PN junction diode. The exact values of the current depend on the nature of the semiconductor and the extent of the doping. Also shown in the drawing is the symbol used for a diode. The direction of the arrowhead in the symbol indicates the direction of the conventional current in the diode under a forward bias condition. For this situation, the side of the symbol that contains the arrowhead has a positive potential relative to the other side. Diodes and other semiconductor devices, such as the transistor, are common components in all of modern electronics, since they allow precise manipulation of electrical currents.